to install more power, increase the thickness of the pipe, so to speak. It's actually to control when charging happens, because if we design for the peak, things get really expensive and we're forced to make trade-offs, versus if we take advantage of the time that the vehicle is spent in the building. In this graph here, we can see the area under the curve is more than enough to charge every vehicle by 6 a.m. And so the theme of today's presentation is I want to unpack what these statements mean, and I want to prove to you how we can do that. Because on a nice clean slide like this, it's very easy to make assumptions. But in today's presentation, I'm actually going to show you the formulas and the math that we use to prove how much power a given building needs to supply energy to any number of chargers. You can see here we highlight you can install up to 10x chargers. That's very well the case. And hopefully by the end of today's presentation, I can show you just how to do that. And so as a very basic example, I want to get some nomenclature out of the way so we're all on the same page before we move on to the formula side of things. But basically, to meet the criteria of install as many chargers as you want, we need to understand what are our constraints. And so the thinking is with switch control, we can control when and how much each electric vehicle is going to pull on the system. We tend to talk in terms of charger capacity to available capacity ratio. And so in this example, if I want 20 chargers, they're all going to be on 40 amp circuits, for example. And this can change based on the model that we pick. But for this example, in today's conversation, I'm going to be referring to 40 amp chargers. Let's say we want 20 of them. That means we need to plan for 800 amps of connected load. But that doesn't necessarily mean we need capacity for 800 amps because of the diversity factor. And what I mean by diversity factor is that not every vehicle is going to be charging at the same time, as well as not every person in the building has the same behavior around plugging in their vehicle. And so in the industry, you often hear the term load management ratios, and that is often referring to the connected load capacity in reference to the available load. So in this example, 800 amps of chargers, 200 amps of capacity gives us a 4-to-1 ratio. And so 4-to-1 is where things start to get interesting for a number of reasons. And we're going to use that as kind of our baseline example because we see it coming up in policy, in requirements for buildings, new builds. And later on, I'm going to show you in terms of wiring, how we can actually change our wiring approaches to best accommodate the load management design, which is more of a software tool. And so I guess the thesis of this presentation is how do we bring this all together? And as a designer of a project, whether you're on the electrical side or just building planning, how can we use these variables to make sure that the building is set up for success, whether they're planning in the short term or long term? So you'll see in the industry, companies make bold claims, including Switch. We say in certain cases we can 10x the number of chargers. And so me being on the technical side, on the solutions engineering team, I definitely have pride in showing how do we do this. It's not just a fancy marketing statement. There's actually math behind it. And so we're going to move over from the nice, pretty marketing slides to, the classic engineering design and standard communication format, which is a nice white slide with lots of fun content. And so I think now's the time we just dive into it. And so when looking at EV behavior, every person, every vehicle, every day is going to be different. And so we need to take that into account. But if we're trying to document this on a piece of paper in a spreadsheet to make calculations, how do we turn that into a finite number or a finite value that we can then use for calculations? And so what I want to talk through today is why we can use probabilistic modeling to capture that EV charging behavior of the drivers. And so a couple points on why probabilistic modeling makes sense. It captures the uncertainty in user behavior. It emphasizes the limitations in traditional average-based planning. And so what I'm trying to say here is if I just take an average value and assume that for every single EV charger, it's not really going to work out because, like I said, it changes driver to driver, building to building, geography to geography, season to season. And what I want to talk through today is how probabilistic models can reduce risk as well as over designing on the infrastructure side, which is where we see our savings long term. And in a lot of cases is the only option to electrify the building. And so the objective of today is to estimate infrastructure capacity pre-install for a multi-unit residential building. And this can also apply for other types of buildings, but for a lot of the context that I'll be using today, I'll just be speaking in terms of multifamily. And so how do we define this? How do we define the amount of energy needed every evening for a building to dispense to the electric vehicle chargers and vehicles? And so just a quick summary of some variables that I'll be referencing. The total energy required by all EVs is our end goal, but we have to then break that term down into a number of variables. So there's one, the energy required per vehicle and per individual vehicle. There's the total number of vehicles. There's the number of charging stalls. There's the time T, which is our available charging window. So this could change for a commercial building versus a multifamily building. Another variable is the total system power requirement, as well as the power requirement per charging stall, which is effectively the charger. And so these are the kind of key variables that we can play with from a system point of view to best meet the design criteria. And as you can imagine, it can get complicated based on preferences of the building, but I've got some examples to go through that. And so further unpacking the energy equation. So to deliver sufficient power to the EVs, we need to make sure that one, the system has enough power. Think of it as the raw horsepower to deliver energy over time T, as well as we need to make sure each electric vehicle charger has enough power. And so the thinking here is, do I want to put in a lot of chargers that are low power, or do I want to put in chargers that are higher power, but they share the available load? And for those that have done projects, this is kind of the level 1 versus level 2 conversation. At Switch, we definitely prefer the level 2 approach, and we'll give you reasons why. And it ultimately comes down to the diversity factor, and it's a better experience for the driver. I'll highlight, just going back to the total time, there are some cases where our total time is not 12 hours. For buildings that are a little bit more constrained, we actually use a design criteria of 8 hours. And by reducing it by a third, we can still electrify a lot of buildings, even if they are 50 plus years old and going through an electrification shift. But basically the working backwards, if we take our P required, which is our raw power of the system, and multiply that over T 12 hours, that gives us the total kilowatts required to charge every vehicle by 6 or 7 a.m., whatever we want to define. And then we break that down per stall. Goes without saying, we don't have to have the same power in every stall, but generally the projects that I see, we are. There are some examples where you might have a couple priority chargers in the visitor spaces that might be 19 or 25 kilowatts for those priority charges. We can also work that into this equation, but for today, we're just going to keep it pretty simple to be conscious of time. Now, statistical distributions are how we can simulate real world behavior. We have to kind of take a trip back to our statistics lecture to kind of refresh our memory on how do we do this. And so when looking at each individual vehicle, we have to plot the probability of how it's going to return home that day. or in some cases, will it even leave the premise that day and require charging? And so these two formulas here are how we do this. And the way we use them is basically plotting over the number of vehicles, let's say 40 vehicles, given a certain distribution, what is the average power required per evening to fuel that vehicle so that it's at 100% the next morning for the driver to take and go on their way. And then there's a number of ways that we can tweak this. And we've definitely done our fair share of tweaking these graphs. But what I found in our work in over 5,000 buildings, log normal distribution tends to represent the average building. And so I've got a couple of graphs here to show you exactly what that means. But basically, this sums up as not everybody is driving 300 to 400 miles a day. They're coming back after doing groceries, after going to work, after running errands, and we actually don't see huge mileage. But that can change per building, whether you're in the inner city versus the suburbs. But you'll see in a moment how that plots out on a graph. And then finally, the distribution, Zed. So our variables are how we tweak this equation based on the input of the property. So if we're expecting, low traffic, low concurrency, our probabilities to influence the distribution tend to be closer to 0.1 versus on the higher end where you have a lot of traffic, let's say it's a public or DC fast charging corridor, our values are closer to 0.7. And so this variable here I wanted to call out of the chances of overlapping charging, because that then influences the distribution and the raw power that we want to assign to the system. And so the way we use it is we'll go and talk to a building and just get a use case for what are they expecting out of the system, and then we can tweak these variables to best reflect what we expect the EV behavior to be. And so let's plot the different types of distribution to see how it looks. And so starting in the top left in the blue graph, normal distribution is okay for some types of problems, but in the case of EV charging, it doesn't quite work out. Same goes with uniform distribution in green. We don't really see drivers all driving the same distance every day. This would work if we were talking fleets, where you've got a standard fleet vehicle, let's say it's a delivery van, and they all typically operate the same routes every day. We can start to see a uniform distribution there. But to go to consumer use, we start to be forced to use log normal or even exponential distribution. And the reason for that is because there's a lot of random activity with just consumer behavior and vehicles. Some days you're coming home with zero battery after a weekend road trip, versus sometimes you stayed home on Christmas Day because you didn't go anywhere, all your family was at home, for example. And so these two graphs I want to call out as the expected behavior, and more specifically, exponential distribution is actually what we see more often than not. And so you can see most people are driving, let's say 50 miles or less per day. And then you do have some people that were on the road, coming home with state of charges on the low end that need, 30, 40 kilowatts to top them back up. And for today's example, I use this one specifically because it best reflects the multifamily. And so we have to ask ourselves, what are we trying to do when assigning probabilistic modeling, and what's our design criteria? Are we trying to solve every single charge no matter what, or are we trying to satisfy a certain percentage of charges every night? And so at Switch, we typically aim for the 95th percentile. And the reason we do that is because as you see a wider distribution of charging in the building, to design to account for 100%, it gets very, very expensive very quickly. And what ends up happening is you end up having a very large capacity sitting idle most of the day because you designed it take into account the last 5% of what's expected. And so I've definitely seen buildings do this that can justify the spend. But for the average multifamily building, this means significant savings if we set our percentile to 95th. And so um, refreshing these graphs, you can see normal and uniform distribution. The mean compared to the 95th percentile are quite tight. This is a very easy problem to solve for, let's say, a fleet or a very predictable use case. But as we get into the consumer behavior, you'll see those two numbers spread, and that's where things get difficult. And so highlighting again the exponential distribution graph, you'll see that if we want to deliver a satisfactory charge to the 95th plus percentile, we need to account for 26 kilowatts on average per port. And going back to those equations I showed further, if the P required per port is higher, the energy required for the building dramatically increases. And so if we cut it off at the 95th percentile, we can start to see savings as we bring down that P required that I mentioned earlier. And keep in mind, these are examples. Every building's different, but I picked these ones to just best graphically show the reasoning behind some of these design decisions. And so when talking statistics, when it comes to EV drivers in this problem specifically, tail behavior is what drives peak load, not the average. And so going back to these examples, it's the outliers that are coming home at 0% and need a full charge that can throw off the equation. And so what we find is it tends to bring up the mean energy required per vehicle per night. And the peak loading events are often driven by these outliers. And so if you recall that graph I showed earlier, going up into the red, that behavior is often caused by those outlier cases, which might only happen once or twice a week or a few times a month, and as well as only for 1 to 2 hours. And so that's when the technology really comes into play, is we're designing for appropriate capacity, but in the cases that we can't design for, load management is there to keep the system safe, as well as share the load and make sure that we're evenly distributing energy across each vehicle. And so the 95% rule is great, especially if we're planning for the future, because it gets us well beyond what's needed, as well as keeps the project within budget. And so if you look at some of the barriers to getting EV charging in the ground, a lot of the time it's high capital cost upfront. And so by bringing down the infrastructure required, we can essentially increase EV accessibility by just getting more projects done, more EV chargers in the ground. And so the takeaway here is, if we want to design for the outliers, things get expensive. And there are some cases where we want to do that, but in the grand majority, we do not. And so we need to consider real world conditions here. The diversity factor is probably the first variable that we're going to play with, according to the research that we've done for the building. And like I mentioned earlier, it comes down to geography, the climate, the season, how close are we to the inner city. Typically, if a project is located in the inner city, we can get away with lower diversity factors versus buildings in the suburbs, buildings in vacation communities typically see a higher diversity factor just because the drivers are putting on more mileage. And so what this comes down to is basically a trade-off or a balance between capital cost and performance. And that's where you, the designer or the project planner, needs to really have an ear to the ground for what the customer is looking for. And so it's a trade-off. If you want the performance, let's say you want full speed all the time, you're going to have to pay for it, but that's okay if the building's willing to accept that. Same goes with public charging. The faster we want to charge, the more expensive it gets. And so that's why we believe here at Switch that the research needs to be done to make sure that we're delivering projects that align with the motivations of the building or property. And so let's talk example. So in this example, we're going to set our initial variables. Let's say we were talking to the customer and they gave us the design criteria of 40 vehicles are going to be in the building, and they want to install one charger per vehicle, 40 EV chargers. And the behavior that they want to design for is between 10 and 6 p.m., they want to charge every vehicle to 100% within a certain means. And like I mentioned earlier, for buildings that are a little bit older, we tend to bring back our time variable T from 12 hours to 8, just because we find that the infrastructure tends to be a little bit more constrained. And so by reducing that variable, it gives us a little bit more performance to play with. For each charger, they're going to pick a 32 amp charger, which gives us about 7 kilowatts per. But these drivers in the building happen to drive a lot. And so we're going to apply a diversity factor of 0.7 just to show you what happens when we stress the system. We, again, chose exponential distribution for this model. And on the right-hand side of the screen, you can see how that is plotted. We have a mean energy of about 13.6 kilowatts, but we do have a few drivers that regularly come home on a depleted battery. And so we need to account for that. That definitely shifted the mean up quite a bit. And so mean energy is kind of within reason here. Most buildings that we see across North America tend to fall between 13 and 18 in terms of the mean energy consumption per evening. And keep in mind, this mean changes Monday to Friday, Saturday to Sunday. And so it can be hard to best predict this, but the idea here is that typically the Thursday, Friday crowd where people are commuting as well as charging up for potentially a weekend trip is what we want to consider. And so what this gives us by using these variables is a total energy required overnight between that 8-hour charging window, which is about 516 kilowatt hours. And so if we wanted to squeeze the most juice out of this system, we would basically divide 516 by 8, giving us 65 or approximately 65, and then dividing that by 40, which gives us 1.6 kilowatts. So this, although we are installing 7 kilowatt chargers, in a worst case scenario, if everybody's plugged in and driving, or plugged in and at home and requiring a charge, they're going to get 1.6 kilowatts. But that being said, with a high diversity factor, we can expect load management to kick in and throttle down from 7 kilowatts, anywhere between 7 and 1.6 in this case. It's important to note that the chargers will not always charge at 1.6 kilowatts. It's a question I get a lot where it's, why am I going to spend all this money just for 1.6 kilowatts per port? This is in a worst case scenario. Most of the time, probably 29 to 30 days per month, you're going to have the charger operating close to 7 kilowatts because some people get home early, some people get home late. There's plenty of time in the day to account for filling those vehicles. But in our design criteria, we're assuming a worst case scenario of I have to do it within 8 hours. And so practically speaking, for the engineers on the call or the people on the electrical side, how do we wire this? And what variables do we have to play here? And so if we look at the ways we can wire each 7 kilowatt charger or 40 amps, we can do it one of two ways. We can give each of the 40 chargers a 7 kilowatt 40 amp circuit, all coming back to 1 or 2 panels. This tends to be the preferred scenario because there's more diversity and you ultimately get better performance on average as a driver. But if we're looking at a more aggressive scenario where budget's a concern and you want to electrify the 40 spaces, but we're trying to limit the amount of labor as well as conduit and wiring, what we can do is we call circuit sharing. So we can put 4 chargers per circuit, and that would limit the number of circuits you have. And so compared to the 40 before, we basically reduce it to 10 7 kilowatt circuits, and you're going to experience savings on wiring as well as labor. The trade-off here is you've got less diversity, in a higher probability of the charger throttling, although the system is not globally constrained. And so what I mean by that is, let's say me and my neighbor happen to be on the same circuit and we both happen to be higher mileage drivers. We would both be sharing that 40 amp circuit, getting 16 amps each, although the system is not constrained. And so that's the trade-off where you might have drivers experiencing a load managed charger, although globally you've got spare capacity. And so in this case, the bottleneck is actually the circuit. And so going back to the dedicated circuit approach, that's the benefit, is because everybody's got the pipe, so to speak, to give them the 7, and they're only going to see a load management scenario when you see a global constraint on the system. Now, this is what circuit sharing and dedicated looks like. And you can see here, if one charger is charging, they get the full power, versus if 3 or 4 are charging, they split it evenly, versus with dedicated, it's one circuit per. But that's not the only way we can wire chargers. For a lot of new builds and new projects, we're often putting in a new panel. But for existing buildings, how do we make use of what's existing in terms of panels and infrastructure? And so at Switch, this is where we incorporate additional layer of technology, which is what we call our CT and switch control solution, where we can put a CT clamp on an existing panel, install chargers on that panel, and the chargers will only pull the remaining capacity of that panel when we detect that there's available load. And we do this every second. And so as the HVAC, the lighting, the other loads in the building throttle up and down on that panel, the available capacity to the EV chargers will also throttle up and down. We see this being as a very effective tool to get EV chargers in any existing building. And that's because we don't have to add a new panel. All we're adding is new circuits and connecting to that existing panel. And so we see a lot of success here, especially given that for the EV charging landscape, getting those first chargers in the building buys you a lot of time to make long-term capacity plans. And so that's typically the strategy we apply with existing buildings, where they have EV drivers in the building today, and they just need a couple of chargers to get started, satisfy the drivers, and then that buys them a couple of years to plan for the big installation. We can take it a step further by adding another set of CT clamps on the building distribution panel. And what that allows us to do is start to curtail chargers and change that global limit of the system based on the output of the entire building. And the thinking here is we're adding this CT clamp to more be efficient on the electrical consumption side of things, especially if you're in a utility territory that charges demand charges. And so the benefits here are, if you've got a time of day or even a load profile that you want to stay within for energy savings, we can mirror that in the switch control setup so that your building stays within the bounds no matter when people plug in their vehicles. And so to summarize what we've talked through today, if you're designing a EV charging project, we want to take into account the following in the pre-design conversation: load calculations, the ones that I showed you today, the panel sizing, how much power can we draw per panel, as well as utility demand charges. We want to consider all that because that'll influence whether or not we need to apply load management. In most cases, we do. And in terms of the output of the work to the customer, you want to be able to provide a per day load envelope. So, hey, customer, between the hours of 10 and 8 or 10 and 6, we're going to design the system to output X kilowatts, which equates to about Y kilowatts per charger. And that way they can start to think, okay, how many kilowatt hours per vehicle am I going to deliver? And pass that information on to the driver so they know what to expect. And it's also important to give them some confidence for, how often are they going to experience load managed scenarios, as well as the variables in the equation are very important assumptions that influence the design. And so in my case, I tend to be very transparent for what variables we're using so that they understand that we're taking into account their use case. Future proofing can put a stick in the spokes in terms of design because it tends to bring up a lot of the what if questions. But my rebuttal to those questions is often, if we have the capacity, we don't necessarily have to be concerned because with switch control or the load management technology, we can share that load evenly. And so it tends to reduce that conversation into just a simple capacity conversation, which tends to be quite successful. So in terms of today's presentation, what are the key takeaways? EV behavior is not fixed. There is often a distribution of behavior over the course of every day, day of the week, season, geography. Probabilistic modeling is the most accurate way for us to do this because we can take into account the different variables per building. We can prevent overloading with load management technology, and with switch, we call that switch control. But most importantly, we avoid overspending. One of the killers of EV projects in general is just the price. And so if we can reduce the infrastructure costs, we can get more chargers, making it that much easier to drive electric vehicles. We can talk through the charger to transformer ratio and how to optimize that. Today we talked in kilowatts, but if you're an engineer, you tend to want to convert that into kVA. So how many kVA per charger do I need to design for? As well as communicate those design considerations to the building and the customer. It's important to explain the why behind all of our calculations because we need to show that we're doing our due diligence in terms of setting the tenants up in the building for success long term. And so with that, I will open it up for questions and we can continue the conversation and hopefully dive a little bit deeper into any particular areas.
All right. Well, thank you, Thomas, for that really great presentation. Boy, I know that just creates a lot of questions in my mind I'd like to ask you. And maybe I'll start with one of my own. As I was seeing all the variables that you're talking about there and the various, how old's the building? Where's it located? How far are people driving? I was imagining that like government regulations that are coming down at like national levels or